All right, so welcome to the sixth lecture where we'll be studying the hypothesis testing in some more details. Okay, so last time we started this topic, and today we'll sort of dig deeper in this, and we'll be studying some more related tests, and we'll be learning a lot of new concepts. Okay. So let me show you what we had last time. So last time we ended with this large sample test for the mean. So what we had is we had x is a random variable with mean mu and with some finite variance sigma squared. So then the I mean we are testing the hypothesis this mu is mu zero, which is some fixed value, against the alternative that mu h1 is mu is bigger than mu zero. So what we did is we drew a sample which is x1, x2, xn with sample mean x bar and sample variance sigma squared. And the idea is we'll reject H0 in favor of H1 if X bar is sufficiently large. And we are assuming that for a large sample, this is approximately following a normal distribution. And hence, I mean, with the approximate size of the test or the significance levels alpha, we can reject H0 provided this is true. And from there, we can derive the power of the test. So this is the first thing we did. And what I forgot to mention last time is we had this statement, like suppose we know that value of sigma. Okay, so know the value of sigma. Okay, why is it necessary? Because remember that I'm trying to compute the power of a test, which is under the alternate hypothesis. And under the alternative hypothesis, we don't know what this mu is. So under the null hypothesis, mu is mu sub zero, but under the alternative hypothesis, mu is bigger than mu sub zero. So how do you compute S squared? Because for computing S squared, you need to um, use some X bar, which is based on the sample. And here, since we don't know, if we don't know, like if we don't have a good idea if that sample mean is really mu sub zero, then we are in trouble, right? One way to do it is using this, like when you assume that sigma is known and gamma mu is given by this one, which we did last time, and then we computed the power of the test with this one, and we ended here last time. Okay, so now with this, let's get started. So suppose let's a very special case that we did last time, which is the approximation with the large sample. But suppose we have uh, let us consider that X actually follows a normal distribution with mean mu variance sigma squared. The last case, we didn't know that, right? So now suppose we want to do the following. So we want to consider the hypothesis. So we want to consider the hypothesis that H0 is mu sub zero versus we are considering H1 to be mu is bigger than mu sub zero. Now, as we know that since this X follows normal, so we can have a sample, draw a sample as we have done before, say X1, X2, Xn. Okay. And we compute the sample mean, X bar, and the sample variance, S squared, right? Compute X bar and S squared. I'll not write what these are. I mean, you all know it by now. So the intuitive, so now as we have done before, so we already know, so several times you've seen it, we already know this, remember, this is one of those theorems in the T distributions. So then this test statistic T, which is given by x bar minus mu 0 over S over square root of n, has a T distribution, has a T distribution with n minus 1 degrees of freedom. Right? That's something we already know. So basically, we can consider this in the following way. So using the distribution of T, we can reject. So here is a decision rule. Decision rule based on significance level equals to alpha is, we can write reject H0 in favor of H1 if this statistic T, which is something that we just constructed, is big enough, which is, in our case, since the significance level is alpha, or degrees of freedom n minus 1. So this is the, okay. And that's it. So this is the t-test for the null hypothesis H0, which is mu 0 equals to mu equals to 0. So this is the t-test for the null hypothesis H0, which is mu equals to mu 0. Okay. Let's see an application. So let's see some applications. And for that, at first, what I'll do is I'll refer to one of the very famous problems, which was discussed in the textbook. So here's an example. So this problem was, as it's mentioned in the book, it was like the data set will be taken from one of the very famous old work of Charles Darwin. So this is example by, it's Charles Darwin, and it's an old one, 1878. So what he did is he was trying to see the heights of a certain species of plant, Z maize plant, to determine the effect of cross-fertilization versus the self-fertilization. Okay, I'll not go into details of this thing. So basically, what was done is there are a bunch of like so there are two random variables which are x and y. We can call it x and y. So the first one is the length of the cross-fertilized plants, and y, so say y is the length of the self-fertilized plants. And so what was done is each of these plants were So there are 15 pots. Okay, 1, 2, 3, 4, all the way to 15. So it's a first pot, second pot, third pot, fourth pot, 15th pot. And in each of these pots, we have one crossed fertilized. So let's write it CF and SF. So here is a cross fertilized plant, and there is a self fertilized plant. Okay, so that's the picture. Okay. So so there are 15 pots, and after some days, the heights are noted. So what's the goal? The goal is to see if the cross-fertilized plants are taller than self-fertilized plants. Okay. Now let's see how we can do it. So first of all, basically, before, since we are mentioning this, so let me just put the data set from the textbook. So here is the data. So for the cross-fertilized plants, for the first one, it's 23.5. I believe they're in some units. Let me check the unit. Okay. I believe they're in centimeters. So this is some of the well, these are the cross-fertilized plants heights. So 1, 2, all the way up to 15, and these are self-fertilized plants height. Okay. Let me just follow up with this example. This is the first of all, what we do is verify, find the student T statistic in this case. So we have like we are given with a set of data, and we are trying to verify the student T statistics. By the way, I forgot to mention what is the null hypothesis and alternative hypothesis. So here we can say that the null hypothesis is H0 is mu equals to 0 versus H1 is mu is bigger than 0. What is mu? So mu is the difference between the heights. So mu is the difference between the heights, average difference or expected difference, expected value of the difference between the heights of a cross-fertilized and a self-fertilized plant. Okay. So that's what we're trying to check. If if the cross-fertilized plants are taller than the self-fertilized plants. Because if mu is 0, so that means that would say that the expected value is the same. So basically, there's no difference. However, if this is positive, that means that will help us the conclusions. Okay. So let's compute the test statistic. Okay. So what we need to do is what is the T statistic? So let me just compute this. So note that when I compute the T statistic value, so T would be X bar. So X bar minus, so under the null hypothesis, it's 0 over S, the the standard deviation over square root of n. So it's okay. So how do you compute this? Now let's look at the numbers. So how do you compute x bar? So x bar would be, for this particular sample, I have 15 samples, so it's 1 over 15. And then compute the difference. For example, the first one is 23.5 minus 17.375. Then, so that for the first one, I take the difference. For the second one, I take the difference plus 12.0 minus 20.375 plus 21.0 minus 20.0 and so on. I'll not write all this. You get the idea. So I'm taking the difference and I'm just writing it all the way up to the end. So it's 12.0 minus 18.0. Now this difference is x bar, right? What is s squared? So s squared is the sample variance. How do you compute it? It's basically 1 over n minus 1. Okay, by the way, so if I compute x bar, so that is going to be, if I compute this number, I have that number computed, and you'll find this to be 2.62. Okay, so that's x bar. And sx is s squared would be 1 over 14, and then you know the formula, so it's basically x minus x1 minus x bar squared plus x2 minus x bar squared plus x15 minus x bar squared. X bar is this one, and x1, x2 are the values that you found. Remember, these are the difference. So this is my basically x1. So this is x1, this is x2, this is x15, this is x3, and so on. Okay. So from here, I can now, of course, compute S, and if you did that for this particular data set, it will be 4.72. X bar would be this one, and S will be this one. And N is, of course, 15. So if I compute this T value, so it's basically 2.62 minus 0, why 0? Because under the null hypothesis, not the null hypothesis, so under null hypothesis, mu is 0. So this is 2.6062 minus 0 over 4.72 over square root of 15, which is about 2.149. So this is the T value. Okay. First thing done. Now, what do you want to do with that? So based on this T value, so we want to conclude something. So we want to conclude we want to test the hypothesis. Now, observe that if we have T of 0.05, 14, this is the value of the test statistic that we, so that means the confidence interval, so the confidence level is 5%, and this is the degrees of freedom is 14. So what we really need to do is basically, I mean, I have, last time I posted how to compute this value, and this value is 1.76. Sorry, I kept saying confidence interval. It's what I really meant is a significance level. Okay, so it's a significance level. And this is the degrees of freedom. So 5% significance level, and this 14 degrees of freedom, we know this value is this one. So what do you conclude? So the conclusion is, so now of the, so hence, but so 2.149 is of course bigger than 1.76. So this is the value that we computed right here, and this is significance level. So this is bigger than, therefore, and hence the conclusion is, thus we reject H0 and conclude that cross-fertilized this particular plant, Z maize, are on average taller, because what was the alternative hypothesis? Remember, so the alternate hypothesis was here. Mu is bigger than 0, so that means mu was the difference, the expected difference. So that means on average, this is taller than self-fertilized Z mass. Okay, done. So this is from one of the very famous data set, which we just discussed. All right, let's see. So now we almost understood all these topics. Let me try to solve a couple of more problems, and then we're done with this section. So this is from exercise problem number 4.5.3. It goes like this. It says that let X have a PDF of the form f of x theta is theta x to the theta minus 1. Remember, theta is a parameter, so it's usually x, but we don't know what this theta is. If you know this is basically a PDF for some 0 less than x less than 1, and 0 otherwise. That has a PDF. Then I can check that the probability density function for this one is if I integrate between 0 and 1, no matter what theta value you take, it's always 1. Where maybe we have reasons to believe that theta can either be 0 or theta is 1. Another way of writing this is theta such that theta is 1 or 2. Sorry, theta is either 1 or theta is 2. To test the hypothesis, H0 is theta equals to 1 against the alternate hypothesis, H1 theta equals to 2, we use a random sample. X1 and X2, we have just two samples of size 2, of size n equals to 2. Define the critical region for this test to be, for some reason, say C is x1, x2, 3/4 is less than x1 times x2. Suppose we are defining this critical region for some reason this way. The question is, find the power of the test. So that's the question. So let's do that. So here's the solution. We are given that this x1 and x2 are sampled, right? So by definition, that therefore this x1 and x2 are independent and they are taking values from this distribution, this one. Okay. So let's see. So since this x1 and x2 are independent, being the sample, the joint intensity for x1 and x2 would be, I can write this as f of x1, x2 to be simply the product of these two, right? So this is basically theta squared, x1 to the theta minus 1, x2 to the theta minus 1. Okay. If you don't, I mean, if I want to match the notation of the previous one, it's basically x1, x2 theta. So that is the quantity of f of the joint distribution. So now, if I want to compute the power of the test, uh, for a general theta, what does it mean? It means it's the probability of rejecting, so basically so let's compute this quantity first. So the probability of rejecting the null hypothesis, which is given by gamma of theta, which is really p of x1, x2 bigger than 3/4, right? For a general theta, okay. I am not really comfortable saying this as the power of the test. So basically what I'm trying to do is for a general, let's compute this one for general theta. So let's compute this gamma theta, which is defined as, say, this one. Okay. How do you compute this? Well, it's multivariable. So there are two random variables. So they're independent, and we have done a lot of these things previously. It's we have to integrate the joint density function. So if I did that, it'll be integration of theta squared x1 to the theta minus 1, x2 to the theta minus 1, dx1, dx2. What is the region? The region is x1, x2 more than 3/4. So basically, if I just stick to x2, so x2 is more than 3/4 x1, and its upper limit is always 1 because of this. So I can write this as x2 is 3/4 x1 to 1, and my x1 can be, its least value can be 3/4, and the highest value can be 1. If you're not comfortable, just draw this region. Okay, so if you draw this region, you'll see that this is how exactly you integrate. Okay. I'll skip this computation and I'll simply write the final result. So this is going to be, after some computation, this will give me gamma of theta equals to 1 minus 3/4 to the power of theta plus theta 3/4 to the power of theta log of 3/4. Sure, check. You can check, it's just the integration of this one. Okay, so therefore, let's see what we have now. So now when we say uh, theta equals to 1, which is the null hypothesis. And remember, theta equals to 2, that is the alternate hypothesis, right? What is this quantity? So this quantity P of x1, x2. So what is gamma of 1? So that is bigger than 3 over 4 under the null hypothesis, right? So that is gamma of 1. 1 is, so this h1 0 gives gamma of 1. And isn't it exactly the significance level? So this is nothing but the significance level. Versus here, gamma of 2, which is probability of x1, x2 more than 3 over 4, and 2 is the alternate hypothesis, so h1. So this, once again, so this is the power of the test, right? Now, we have already computed this longer expression. So therefore, we found that gamma of 1 is, if I just plug in theta equals to 1, and gamma of 2 would be when I plug in theta equals 2, so it's 1 minus 3 over 4 plus 3 over 4 log 3 over 2, 4. So that is the significance level. And gamma of 2 is 1 minus 3 over 4 squared plus 2, 3 over 4 squared log 3 over 4. So this is the power of the test. So actually, this problem is asking you only to compute this one. So this is the answer. But I wanted to show you this one because, just to compare the symmetry, like basically we got both the answers. So we also obtained the significance level, which is gamma 1, power of the table, test, which is gamma 2. It just be a little bit careful for this example, sort of tweaked the notation a little bit because usually we used gamma for the power of the test. But note that, I mean, if I have gamma for h0 when h0 is true, that is exactly the significance level. So this gamma under the null hypothesis is nothing but the significance level, and that is something we found. Okay, so that is this one. Let's do one more, which is, say, the next one. Here's another example. And this is problem number 4.5.4. So it goes like this. Let x have a binomial distribution with n equals to 10 and p equals to either 1/4 or 1/2. So we have to check the hypothesis 1/4 or 1/2. So the hypothesis, all right, okay, the hypothesis H0, which is p equals to 1/2, is rejected and H1, which is p equals to 1/4, is accepted if the observed value of x1, it's basically a random sample of size 1. We just draw it once. A random sample of size 1 is less than or equal to 3. Okay, so what is the deal? So x has a binomial distribution with n equals to 10, and p can be either 1/4 or 1/2. Now we just draw a sample, and if this sample is less than 3, we reject the null hypothesis that h equals to 1/2, and we accept the alternative hypothesis that h is p equals to 1/4. Okay. So that's pretty simple test. The goal is find just like the last problem, find the significance level and the power of the test. So the problem is very similar to the previous one, in the sense that in the last problem, you're also finding the significance level, power of the test. Here, the same thing. Okay, so let's do that. Here, so here's the solution. All right. So what is the level of significance? So significance level is basically, we are saying that the probability that the value of x is less than or equal to 3. Remember, what's the significance level? It's the rejecting the null hypothesis when the null hypothesis is actually true. So basically, this is under H0, right? So that means in this case, P is what? So it can be, so that means with P equals to 1/2, null hypothesis is true. So P x value can be 0, x value can be 1, x value can be 2, and x value can be 3. It's binomial with the 10 trials, success here, p value 1/2, so it's to the 10, 10 choose 1, 1/2 to the 1, 1/2 to the 9, plus 10 choose 2, 1/2 squared, 1/2 to the 8, plus 10 choose 3, 1/2 cubed, 1/2 to the 7. Okay. If I compute this, it is approximately 0.172. So this is the significance level. Now the power of the test is basically the same thing. Is given by probability of x is less than 3, but provided the alternative hypothesis is true. So remember, that corresponds to the correct decision, right? So alternative hypothesis is true. We are actually rejecting the null hypothesis. Okay, so let's see. This is given by, the only thing is, if the alternate hypothesis is true, my P is 1/4. So that is my H1, right? So once again, this is P of x equals to 0 plus x equals to 1, P of x equals to 2, and P of x equals to 3, which is 10 choose 0, 1/4 to the 0, 3/4 to the 10, plus 10 choose 1, 1/4 to the 1, 3/4 to the 9, plus 10 choose 2, 1/4 squared, 3/4 to the 8, 10 choose 3, 1/4 cubed, 3/4. Right? And if you compute this number is about 0.776. So this is the power of the test. Okay. So this some examples which are very good for practice, in the sense that now you'll understand like the meanings much better, right? So what is meant and how it's computed. All right. Let's do, say, one more problem. And this is problem number so this is number 4.5.8. So it is saying the problem goes like this. So let us say the life of a tire in miles, say X, is normal distributed with mean theta and standard deviation 5,000. Okay. Now, past experience indicates that this value of theta is 30,000. So the lifetime of a tire is 30,000 miles. The manufacturer claims that the tires made by a new process have mean more than 30,000. Okay. It is possible it's more than 30,000. Maybe it's possible to have 35,000. It's possible that theta is 35,000. Check this claim by testing the null hypothesis, theta is 30,000, against an alternate hypothesis, theta is more than 30,000. Okay. Now, how do you test it? So we observe, it's still a part of the question. So we observe n independent values of x, say little x1, little x2, up to little xn, and we reject h0 and thus accept h1 if and only if x bar, what is this, the from the sample, the sample mean, x bigger than some c subconstant. Now here is a problem that we're trying to address. Determine n and c so that the power function gamma based on theta of the test has the values gamma of 30,000 is 0.01, gamma of 35,000 is 0.98. By the way, so this is the reason why, so since the power of the test is pretty high here, and that's why we say that it's possible that gamma is 35,000. Okay, but that's an aside. Okay, so our goal here is to determine n and c so that the power function satisfies this. All right. a lot of information are provided. So we have some x that is following some normal distribution that we know. So it is possibly following a normal, it's following a normal distribution with some mean theta and the variance 5,000. And the past experience indicate that this theta, which is the expected lifetime of a tire, is 30K. Now we're trying to check if this is true. Not only that, so we're trying to conclude that this theta is 35,000. So how do you do it? So for 35,000, if the power of the test is pretty high, then that is a good way to choosing that. But for now, what we're doing is we're drawing a sample of size n, and then we compute the average of that, so the sample mean. And if that is more than some c, then we reject the null hypothesis. Okay. Now we are trying to find that n and c so that the power functions are given by these two. Okay. All right. So let's solve this. Here is a solution. So we have gamma of 30,000 is 0.01. Okay. Now let's recall what the meaning of that gamma is. So remember that gamma of theta is really p of x bar bigger than some c under certain theta. So that's the definition. That's something we should remember. So gamma of theta, its definition is the probability that x bar is more than c for predetermined c, and depending on the values of theta, it changes. Now, what about this one? So let's compute this. If this theta value is 30,000, what does it mean? Theta was the parameter that was trying, remember the previous sections, theta was the parameter that we are estimating. And what is the parameter we are trying to estimate here? So that means we are saying that theta is 30K, right? So here, so that means we can safely say that the expected value, so this normal distribution has mean 30,000. If then x satisfies a normal distribution with 30,000 and 5,000. So this is the value of theta. Okay. Now let's spell this one out. So what does it mean? It means again probability of x bar more than certain c is 0.01. By definition, with the value of theta, 30,000. So that means under this condition, we know that the expected value is 30,000. So I can subtract 30,000. And sigma is a good estimator of S. So, or you can just write sigma over square root of n. So I'm just trying to convert this to a standard normal distribution. It's c minus 30,000, 5,000 over square root of n. So that is going to be equal to 0.01 from this equation. I subtract the mean, divide by the variance. Okay. So from here, again, so this is basically, if I compute this quantity, so this is converting to a standard normal distribution. So it's 1 minus phi of, so this is the standard normal distribution. So this number is c minus 30,000 over 5,000 over square root of n is 0.01. Okay, so that means I have phi of c minus 30,000 over 5,000 over square root of n is 0.99. That's one equation. Now, from the z table, find the value of this one so that this is satisfied, and find it that in this case, you can get the equation c minus 30,000 over 5,000 over square root of n got to be 2.325. So that is what I'm trying to say is phi of 2.325 is 0.99. Let's find it from the table. That is my equation number 1. Okay. Now let's consider the other one. So by other one, I mean, so this is one condition that we took care of, but there are two another conditions. Gamma of 35,000 was 0.98. So let's use that. So now gamma of 35,000 is 0.98 once again. Sorry, 0.98. Once again, observe that if, so this is a theta. This is theta. So if theta is 35,000, then really this gamma, this x satisfies a normal distribution with 35,000 over and 5,000, right? And correspondingly, x bar satisfies a normal distribution with the same 35,000 and the variance 35,000 over square root of n, right? So this really means that probability of x bar is bigger than c is 0.98 under that theta, okay? With theta is 35,000. Let me just write it here. So with theta is 30,000 here. Okay. Now, in this case, therefore, we have same computation. So P of x bar minus 35,000 over 5,000 over square root of n is bigger than C minus 35,000 over 5,000 over square root of n. Okay. Same thing as we have done earlier. So this is 0.98. So hence we have, so this is z. So z bigger than something. So it's 1 minus phi of C minus 35,000 over 5,000 over square root of n is 0.98. And therefore we get phi of C minus 35,000 over 5,000 square root of n is 1 minus 0.9 0 0.02. Therefore, we find with this so C minus 35,000 over 5,000 square root of n is equal to minus 2.054 because phi of, again, find it from the table, minus 0.54 is 0.02. Okay. You can actually find this 0.98 from there. You can compute this one. Okay. Good. So this is my second equation. What was my first equation? The first equation was right. So this is the first equation for C and N. And this is my second equation for C and N. Solve 1 and 2 to get N approximately 20 and C approximately 32,661. And these are the answers. Okay. So if there are 20 samples and where we are checking against the value C, which is 32,661, then we have a pretty good power of the test, which is 0.98 for 35,000, and it's pretty low power of the test for 30,000. So it's we can very much take the value theta equals to 35,000 in that case. Okay. So I think that is all about this particular section. Now let's talk about a little bit more. And actually in the textbook, this is in section 4.6, some additional topics. Now, so far, what we have done, it's called the one-sided test, like meaning that we either have, say, mu is equal to, say, 1/2, and we are testing against something, say, mu is more than 1/2, right? So that is something which is called the one-sided test. Let me just write the formal definition of the one side, like the one-sided test and two-sided test, and then we'll go from there. Okay. So what we'll write is the following. So one-sided hypothesis. Okay, so for example, we said that say H0 is mu equals to 30,000 in the last example, sorry, versus H1 is mu is more than 30,000. Now, in this section, we can also start something called the two-sided hypothesis. It's simply H0 is testing it's 30,000 versus H1 is mu is not 30,000. So that means we are not trying to conclude that it's more than 30,000. We simply say it's not 30,000, meaning that there is a possibility that it can be also less. Okay. Now, there are some criteria that you need to know in this case, or some test criteria. So let's discuss that. So for the two-side case. So example, large sample, two-sided test, for the mean. So what we're assuming that x is a random variable with mean mu and variance sigma squared. Note that it's not really necessarily a normal random variable. Sigma squared. Okay. We want to test. So it's a two-sided test. Okay. So we want to test H0, which is the null hypothesis, mu equals to mu 0, against versus H1, mu is not equal to mu 0. Where this mu 0 is specified before. Okay. It may be a number, say 5, 20, 25, whatever. Okay, now here is how it's done. So suppose we have a sample. So it's very similar to the one-sided test. So let x1, x2, xn be a random sample from x. And x bar and sigma x bar is the sample mean, just like before. And s squared is the sample variance. Okay. Now, for the one-sided test, remember how we rejected it? We reject um, the value. So we reject this null hypothesis provided this X bar is too big compared to mu zero, right? Here also we can say that suppose this X bar is too big. It's a two-sided test, so maybe it's too big on the right side of mu zero. So suppose this is mu zero is here, and suppose we are saying that okay, so if your X bar, let's define two numbers. So suppose here it's K, here is H. So if X bar is here or X bar is here, so X bar is less than H or more than K, then we reject the null hypothesis. It's two-sided. Previously, we don't care about that side. We only care about the right side, right? So because we know that X bar is, the other one is X bar is more than mu zero, that is the alternative hypothesis. Here, alternative can be, I mean, it's basically not mu zero, so it can be either this side or that side. So if we can reject the null hypothesis that it's mu sub zero, provided it's more than a certain number or less than another number. So here's the intuitive way. Um, so intuitive way is, our intuitive decision rule is reject H sub zero in favor of X bar, sorry, H1 if, as I drew there, X bar is more than K or X bar is less than H with certain confidence. So we'll have some significance level just like as we have done last time. So where, let's figure out these two numbers. So let's put some values to it, where this K and H are to be selected in such a way that, by the way, here clearly H is less than K, right? We suppose said that the probability that X is more than K or X is less than H, that is alpha. So alpha is probability under the null hypothesis, H0. Another way of writing it is X bar less than H or X bar bigger than K under the null hypothesis is alpha. Okay. So that means probability, I mean, this are two disjoint intervals. So X bar less than H under the null hypothesis, or X bar more than K under the null hypothesis. So if I add these two, I should get alpha. Okay. Now, for the sake of convenience, we can always choose this one alpha over 2, this one alpha over 2. Right? So let's do that, and that's typically how we'll be doing. Okay, so now we observe the following. So for the large sample, after this one, for large sample, this X bar is symmetrically distributed about mu zero, right? Why? Because under, for the large sample, this is basically the normal distribution. So it's symmetrically distributed about mu zero under H0. Okay, because that's under H0, that's the mean. So in this case, I can choose probability of X bar less than H under H0 is alpha over 2. It's just a choice. Okay. And probability of X bar bigger than K, H0 is alpha over 2. Okay. And we can say that we now have that X bar minus, we have done it many times, minus mu 0 over S squared of Ln it approximately follows the normal distribution. So what would be a decision rule? So a decision rule would be to reject H0 in favor of H1 if the value of this one, x bar minus mu 0 over s over square root of n, is more than h of alpha over 2. So what is going on? So basically we have this z of alpha over 2 minus z of alpha over 2. So this region here is alpha over 2, and this region here is alpha over 2, 2. So as long as this quantity is in one of the two regions, we are saying that x bar is far away from mu 0. Okay? So that is the decision rule. Also, let's see if we can compute the power of the test. So for power of the test, power function. So that means in this case, H1 is true. So that means mu is not mu 0, right? So what will happen in that case? So in this case, the expected value is just mu, right? Now, what do you have? So we are rejecting when this is true. So let's compute this. So gamma of mu is probability of x bar minus mu over s over. Okay, so we also assume that, say, suppose we know sigma. Okay? Suppose sigma is known or estimated. So I can write this instead of s over square root of n, I can write sigma over square root of n. So this is the gamma of mu. What is that mu? Mu is for the H1. So mu is the expected value of x bar. Okay. Let's compute this with when H1 is true. So that's why. So you don't see the expression. You don't see mu here, but mu is hidden because mu is sort of in the H1. Okay. So let's compute this. So what we have is following. So in this case, gamma of mu would be probability of, if I simplify that, I have x bar minus mu sub 0 over sigma square root of n is more than z of alpha over 2, or x bar minus mu sub 0 over sigma square root of n less than minus z of alpha over 2. If you simplify this, it's going to be probability of x bar, if I have this one, then it's less than mu sub 0 minus z of alpha over 2 sigma over square root of n plus probability of x bar bigger than mu sub 0 plus z of alpha over 2 sigma over square root of n. Now, remember that this mu is there. So let's try to see the mu. Remember that with respect to mu, once again, for the case of large sample, it's approximately normal. So I can write this P of x bar minus mu over sigma of square root of n. It's less than what? So I'm just subtracting mu and divide by this one. So it's basically it's mu 0 minus mu minus z alpha over 2 sigma square root of n plus p of x bar minus mu over sigma square root of n is, I'm subtracting mu and dividing by the sigma square root of n. So I have this one, right? The first one is probability of, let's call this one, this is approximately for the large sample case, z is less than, when I divide by sigma square root of n, I get minus here. So it's mu 0 minus mu, and then square root of n over sigma, right? Square root of n over sigma minus z of alpha over 2, this first one. This is my approximately normal, approximately standard normal. And here again, approximately this is z, probability of z bigger than square root of n over sigma. If I divide this to mu 0 minus mu plus z of alpha over 2. So in other words, so this is, so the approximate power of test gamma of mu can be written as this one in terms of phi is phi of square root of n over sigma mu 0 minus mu minus z of alpha over 2. And this is bigger than equal to sign, so it's basically 1 minus that thing. So it's plus 1 minus phi of square root of n over sigma mu 0 minus mu plus z of alpha over 2. Done. This is the approximate power of the test. Okay. So this is something which is sort of important for testing two-sided hypothesis. Okay. Let's do a quick example. So a quick example in this case. Suppose we are choosing an example. Say we are having H0, which is mu equals to 30K, versus H1, which is mu is not equal to 30K. Two-sided. Suppose we have n is 20 and alpha is 0.01. So that means the rejection rule, so the decision rule is reject H0 in favor of H1 if X bar minus 30,000 over S over square root of, there are 20 samples, 20 is more than Z of alpha over 2. So that means this is 0.05005, which is 2 point 2.575 from the table or from the link that I provided you. Okay. So that is the decision rule. So now all you have to do is basically you have to find a sample, whatever the sample value. You find the sample mean, you find the sample variance, you computed this one. If this number is bigger than this one, you reject the null hypothesis. If this number is less than 2.575, you retain the null hypothesis. It's a two-sided hypothesis testing. Okay? So this 0.005, it's actually the 1/2 of this one. Okay. So this is alpha, so it's alpha over 2. Okay, I'll do another example, which will sort of indicate the indicate this thing. Let's do this one. So this is something like this one. This is the problem number 4.6.8. Okay, so but before doing that problem, let me just mention one more important concept because since we are mentioning so many things, so we are at this point ready to define the observed. So definition is the definition for the observed significance level. Another commonly known name for this one is p-value. It's defined as p-value or the observed significance level. It's based on a sample. So what is going on? So suppose we see a sample. Now, based on the sample, we are trying to see what is the probability that X bar is more than that X bar. So let's see. Suppose a sample x1, x2, xn is observed. And I'm trying to define the p-value. Observed. And the observed value or the realized value for this particular sample, X bar is summation I from 1 to n xi over n, right? So I take the sample. So the X bar is a number. We ask the questions. The question that we ask is this X bar that we computed is sufficiently large to reject H0 in favor of H1? So the question is this X bar is obtained from the sample, is sufficiently large to reject H0 in favor of H1. So this question is solely asked based on the sample. Okay. So sample is observed. That's the key thing. It's after the sample is observed. Okay. To answer this, first of all, let's check the now we're ready to define. To answer this, we have to define this quantity. Answer that question, we define a p-value. We calculate p-value, which is given by probability of X bar bigger than X bar. What is this? This is a random variable sample mean, and this is the observed one. So this is the observed sample mean, and this is the sample mean, which is a random variable. Okay. Under the null hypothesis. Okay. Another notation for the same thing is P, and then this H0 is written here, X bar bigger than X bar. Same notation. Sorry, these were just two different notations, same meaning. Okay. So this is the it's sort of a data-based significance level. Now, if this value is less than a certain alpha level values, so what happens is, suppose there is a alpha level value is somewhere, say, So suppose this is the critical point. And if your X bar happens to fall here, then you see you can reject the null hypothesis. Or if your p-value, so what does it mean? So the p-value in this case would be this is the p-value. The p-value. So if your observed X bar is here, and then p-value will be here. So if your critical point was here, so then of course you are saying that the p-value is less than the significance level, and in that case we can reject the hypothesis. Okay, so if your p-value is less than um, is less than the significance level, then the hypothesis can be rejected. H0 is rejected in favor of H1. Now, please note that so this is significance level alpha, or alpha over 2 for um, two-sided. Oh, well, it's actually alpha, even for two-sided test. We'll define it later, but okay. So please note that it's a data-based. Like you have to see the sample before you can really compute it. So p-value is computed after you draw a sample. And after you draw a sample, you compute this p-value, and there is a preset significance level. So you compare the p-value with the significance level. If it's less, you reject the null hypothesis. If it's and if it's I mean, yeah. So and that's you reject the null hypothesis and take the alternate hypothesis. Okay. So now we have defined all the quantities that we needed, and let me show you another example, and that will clarify one more topic that I want to say, and that will be the conclusion of this section. And this is problem number 4.6.8, I believe. So here's an example. It's number 4.6.8. It goes like this. Let P equals, I'll not solve the entire problem, but I'll solve part of it. P equals the proportion of drivers who use a seat belt in a country that does not have a mandatory seatbelt law. Okay, so it was claimed that P equals 0.1. So that is the proportion of the drivers who use seatbelt. Now, an advertising campaign was conducted to increase this proportion. So what happens is 2 months after the campaign, y equals to 104 out of a random sample of n equals 590 drivers were wearing their seatbelts. Okay. The question is, was the campaign successful? And we'll do it in three steps. So first of all, let's see. Part A is define. This is the main problem, and we'll be defining the null and alternative hypothesis. Okay. This is simple. So H0, so null hypothesis is previously it was the proportion of seatbelt the drivers were wearing seatbelt was 0.014. So suppose that nothing changes. So P is 0.14. So after that advertising campaign, so suppose P remains 0.14 and HA would be P is more than 0.14. That is, the more people are wearing seatbelts, so it's more successful. B, define a critical region with alpha equals to 0.01 significance level. So that's also not hard. So let's see. What we need to do is, let's see. So we can observe after so what we have we're observing is the proportion of drivers. So this is the observed proportion after the campaign, which is what? Which is basically 104 over 590, which is 0.176. So I mean, for a large sample, which is n equals to 590, it can be considered as a large sample. So I can have a test statistic Z, which is the p hat against what we're testing, which is the original value. So whatever we're testing, 0.14 in this case, over what's the variance of this p hat. So we have done it before. So this is basically, remember that for Bernoulli distribution, it's given by this one, P1 minus P over N. Okay. So that is the test statistic. And the alpha level is given to be, so here the alpha level is given to be 0.01, and correspondingly, Z alpha is Z of 0.01, it's 2.326. All right. So if Z that we computed from here is more than 2.326, then we reject H0 in favor of H1. That means we conclude that there are more people wearing seatbelts. Okay. All right, so this is, we have defined this that second part, and C is determine the approximate p-value and state your conclusion. So the p-value, is equal to probability of z more than um, so 0. So sample mean. Let me just write this way. So as we have defined here, let me just show you. It's x bar is more than um, x bar, right? So what is this quantity here in our case? So basically this would mean that p hat is the test statistic. So sorry, is probability of p hat, which is the um, let me just write this x bar because that's the proportion that is the random variable, which is base more than the observed one, and the observed value is p hat. So this is the observed proportion, which is the mean, right? And this is the sample mean as a random variable under H0. So let me just write H0 here, which is same as writing this given H0. Okay. Now we have completed everything. So P0, so this is basically X bar minus under H0. The mean is P, right? Which is 0.14 over square root of 0.14, 1 minus 0.14, and how many samples are there? There are 590. So this quantity, and that's got to be a normal. So it's now p hat. So this value we have already found to be 0.176 minus 0.14. This is p hat is 0.176 over square root of 0.14, 1 minus 0.14, 590. Okay. If you compute this, this is going to be probability of, and this now approximately, and that's why this word approx comes. So this is approximately z is bigger than, if we compute this, it's approximately 2.52, which is 1 minus phi of 2.52, which is approximately 0.00587. So that's the p-value. So p-value is based on the sample. So this is the observed value. So that is something we observed. So what is the part that is, or what is the probability that the sample mean is actually more than the observed value of the proportion, right? And therefore, conclusion, since p is less than alpha, and alpha was 0.01, therefore H0 is rejected. So, and we conclude there is sufficient evidence to show that the campaign was successful. Yeah. Okay, so that is it. So we studied the two-sided hypothesis testing, and at the same time We understood how to compute the phi value. We understood how to compute the significance level, and that's how we computed all these quantities. Okay. So this is all about this hypothesis testing, the introduction. So next time what we'll be starting is we'll be doing chi-square test, and we'll be discussing that. So stop here. Thank you.